Yeah, you can go ahead, Roberto. Roberto?
Fue embora.
Okay, maybe I will be the. He left. All right.
Yes.
It
Okay,
seems
so
that
may I welcome. So welcome to GADEPS. So today we have Yves Martin, who is going to talk about non-vanishing of Fourier coefficients of Siegel cusp form. Okay, so Yves.
Thank you very much for the invitation. I'm really happy to have the opportunity to speak to you and tell you some things about my latest work. Actually, this is work in progress. It's not completely done, but I have some results that I can show you and tell you a little bit about what I think one should get at the end. So uh, please interrupt me whenever you feel like. And let me show you first, then introduce some notation, and then in a few more minutes you will see what the problem is and what the motivation behind this work is. Okay, so let me see. Okay, here. This work is about Siegel modular forms. So let me recall some of the basic facts and notation for this in this subject. We take the analog of the complex Aberhaf
sorry.
plane.
If you are passing the slides, at least I am not seeing that.
Oh, you don't see it? I already passed one.
Uh, I don't know. Maybe it's
You are now.
okay.
Now, okay.
Yeah.
Do you see it now?
Yeah.
Yes. Yes. No.
Okay, this is so. This is the first page, right? Or the second page. So I'm introducing some notation where so we can talk about Siegel modular forms. Hn is the analog of the complex Aberhaf plane in this more general setting. So n by n complex matrices, which are whose transpose is equal to itself, and whose imaginary part, which is a n by n real matrix, is positive definite. Okay, so that's one ingredient, and the other one is this group gamma n, which is a symplectic group of size 2n with integral coefficients. So these are 2n by 2n matrices with the entries in the integers, and such that if you do this, m transpose Jm is equal to J, where J is this special matrix 0 identity minus identity 0. We will always write this matrix M in this group in blocks, A, B, C, D, each of them of size n by n. Can you see the pointer?
The pointer?
This hand that I'm sort of
No,
using.
I don't.
Are you moving it or it is?
Yeah, I'm moving it. Yeah, probably you don't see it. Okay.
No.
The hand is
Just to
fixed
know.
actually. This mouse.
Okay. All right. It's okay. All right. Now, this group acts on this complex analytic manifold in the following way. C goes to MC, where MC stands for AC plus B, this n by n matrix, multiplied by CC plus D inverse, another n by n matrix. Okay. And the other thing that we will use or we need is this congruent subgroup of gamma n, gamma 0n, big N. All the matrices in the group gamma n, where C is congruent, the block C is congruent to the block 0, mod this integer big N. Okay, so these are the main ingredients. So in order to, we want to study some functions in this setting. So let me introduce those functions. Can you see that slide?
Yeah, I think there is some 4 seconds of time difference when you switch the slides. So now we don't see that. We still see the second slide.
All right,
gamma
but then I mean you can see it now.
Ah, okay,
right?
no, okay, yeah, no.
Okay, yeah, I try to I try to take care of that too. Okay, so for any integer k, you have an action of the group gamma n on the space of holomorphic functions from Hn to C. Namely, if you have f from Hn to C, and you have any matrix M, you construct a new function, f slash m, and it's given like this. Like this is established here. You take this factor, determinant of cc plus d to the minus k, and you multiply this by f evaluated at mc. Okay? This is an action of the group on functions defined on the space Hn. And there is a second action that I need to know. And that has to do with the action of a subgroup of M, because now it's indexed by no integers but half integers. So if k is greater or equal than 1, there is an action of the group gamma 0, 4 on the same space of functions. And what it does is the following. Take a function f, take a matrix M, now on gamma 0, 4, and construct a new function from Hn to C, which is the one that you get when you multiply this special factor here, this quotient of theta functions raised to some power minus 2k plus 1 times f evaluated at mc. So it's very similar to the previous one, except that now the factor in front of f is different. And it is chosen in such a way that this corresponds more or less to the square root of to the square root of the factor used before for integral k. So you can see the quotient of theta function square is equal to the determinant of cc plus d times a plus or minus 1 given by this Kronecker symbol. Okay, so what we have so far, we have a group, we have functions from Hn to C, and an action of this group now on functions, not only on the points of on Hn. And we need those actions because we will define Siegel modular forms of integral weight and half integral weight using those actions. Namely, we will do the following. First, we pick a parameter kappa that is an integer k, or is an integer k minus 1/2. So it's an integer or a half integer. And we take any Dirichlet character chi, mod big N. And with that Dirichlet character, we will build a character for the group gamma 0 n. Okay, and that's chi of m equal to chi of determinant of d, this block in the matrix M. And now we can define the main the main role in this situation. A Siegel cusp form of weight kappa and character chi over the group gamma 0 n is any holomorphic function from Hn to C, such that when you act with the group gamma 0 n, you leave the function invariant. So a Siegel modular form is just that. But now we want something else. We want to work with Siegel cusp form, which is a subset of Siegel forms, and which is sort of is a mysterious part. And those are the Siegel modular forms such that vanishes at every cusp of gamma 0 n. I'm not gonna talk about this condition. One can be very explicit about that, but we will just assume that this f that we work with has that property, because the only thing that is relevant for us in this situation is that you can write this function as a Fourier series. So let me first say that the set of all functions which I just defined, Siegel cusp forms of weight kappa and character chi over gamma 0 n, they form a finite dimensional vector space, and such a vector space is denoted in the usual way S lower kappa upper n big N character chi. Okay.
Maybe one question: what was the reason you substituted the classical automorphic form CZ plus T with this expression of theta series? I mean,
That's for the because you use half integral way, because it's not. I mean, there's a problem with the plus or minus sign, since you have to take the square root of CC plus D.
I see. Okay.
You have to be careful with that.
Also, the
And
character chi is not entering to your definition.
Exactly. The character chi is just accessory. The multiplier is completely taken care of when you take this quotient of theta functions and you restrict your action to gamma 04. I believe that you can do something like that if you, I mean, I'm sure you can do this also for the full group if you go to the metaplectic cover of the full group, SP of gamma n. But the formulas are less explicit. So that's why you restrict to a subgroup of gamma n, namely gamma 04, and then the multiplier becomes very explicit, this quotient of theta functions. Okay, is that clear?
Okay, thank you. Oh.
Perfect. Okay, you will see that I want to do something about Siegel modular forms of integral way, but I need to use the other ones, so that's why I have to introduce them too. Okay, so the important thing about Siegel cusp forms is that they have this Fourier expansion. This E to a matrix, E of TZ, I mean, the E to the matrix X means E to the 2 pi I trace of X. So this is just short notation for that function, exponential function. And these CFT are just coefficients. And T is the index of these coefficients and runs on the set of symmetric, half integral, positive definite n by n matrices. If you do all this in the classical case, this T will be just positive integers. That will be the index set. So 1 by 1 matrix, positive definite 1 by 1 matrices if you want. But in this more general case, the index set is more complicated. Okay? So I'm saying something obvious and trivial. If you look at all the coefficients CFT, where T runs on this set of indices, n by n positive definite half integral matrices, you determine F completely, which means if you have another Siegel cusp form with the same coefficient, with the same Fourier expansion, then they are the same. So determines completely the Siegel modular form. But also it's true that F has a Siegel modular form, has many symmetries. Therefore, all these coefficients, there's a lot of redundancy here. There's too many coefficients. You don't need all of them to determine F completely. So, for example, you can take the coefficient of F at T and also at the matrix G transpose TG. and the coefficients are the same. So for all G, a matrix in SL n Z, you can take the conjugate of T by this action, and the coefficients are the same.
Mm-hmm.
And that's the reason for that is that F is a Siegel modular form. Therefore, it's invariant than this particular matrix G00 G transpose inverse. So because F is invariant and this action, you can deduce that the coefficient must satisfy this rule. Therefore, this collection of coefficients is just too much for identifying F completely. Hence, we're interested in subsets of this set of indices, something that we call lambda n. Delta n, sorry. Delta n. This is a subset of Jn, and I want to point out the following statement. You have two cusp forms of yk, integral yk, over gamma 0 n of the re n, small n, character chi. And this set lambda n is good if you know that if the Fourier coefficients of these two Siegel forms are the same at all t's in this subset, then they have to be the same. So in some way, I'm looking for a subset of the index set, which is good enough so you can identify the Siegel modular form just by looking at the coefficient indexed by these elements in this subset. Well, this statement that says that this lambda n is a good subset is equivalent to this other statement. The second statement says if you have a Siegel cusp form in the same space and you know that it's non-zero, then there must be some t in this subset where the coefficient is non-zero. So here you have a statement about non-vanishing of Fourier coefficients of Siegel modular forms that tell you something interesting, that says you can identify then a collection of matrices which index enough Fourier coefficient so you know when the functions are when the Siegel modular forms are the same or not. Okay, so if you want to find a good set lambda n, you can find a set where you know that if f is non-zero, then a Fourier coefficient indexed by an element in that set is non-zero. Is that clear?
There is any reason that you concentrate on just cusp form, or?
Essentially because the other part of Siegel modular forms are given by Einstein series.
Okay.
And therefore, it's more complicated than the situation than in the classical case where you only have one type of Einstein series. In this case, you have different types of Einstein series. But nevertheless, it's easier to handle those. So the cusp forms are the mysterious part.
So this must be related also to the dimension of the space of cusps or the fixed weight, no? Or not?
Right, absolutely. Of course, when k is getting bigger, the dimension is getting bigger too. And of course, if you are dealing with gamma 0 n, it's a lot of different subgroups. So this is a problem that is that admits a big variety of situations. Now, notice that this lambda n is something that I want to describe independent of the weight and independent of the level of gamma 0 n, of this big N. So it should be something that works for all k's and all n's. Okay, and so that's the problem, to find this good lambda n. So let me tell you something about the history of the problem. But before that, I have to tell you something about a definition. That a matrix T is half integral means that if you take twice the matrix, you multiply the matrix by 2, then all the coefficients, all the entries in the matrix are integral, are integers. And also the diagonal, the main diagonal, only has even entries. Okay? So once you have that situation, you can look into the entries of the matrix, the small Tij, and compute the GCD, the greatest common divisor of all the entries in this matrix 2T. Of course, you divide by 2 in the case of the diagonal entries. And you say that T is primitive if the GCD is 1. Okay? Okay, then the first result about the problem I just showed you in the previous slide is due to Saguier, who says that if you take n equal to 2, so in the degree 2 case, so Siegel modular forms for gamma 2. If you take the set of primitive 2 by 2 half integral positive definite matrices T, then this is a good set in the sense that if you have two Siegel modular forms, cusp forms for gamma 2, and if you look at the coefficients indexed by this type of matrices, then you can distinguish the Siegel cusp forms. So for 2 and big N equal to 1 and character trivial, this is established by Saguier. Actually, it's just 2 or 3 lines in a paper of Saguier of around 1980 or something like that. After that, Yamana showed something much more general in the same sense. If you take all matrices T such that its GCD divides this big N by the conductor of the character, then you have a collection of matrices T, right? Where this property holds, the GCD of T divide this fixed number N divided by the conductor of chi, then this is also a good set. Of course, that's much more general, applies to matrices, to Siegel cusp forms with integral or half integral weight. So there's a kappa here. So it's much more general. It's also for groups of type gamma 0n and non-trivial characters. So it's much more general than that Saguier's result. Okay. And then there is similar result by people like Bollman, Conan, Hein, Ibukijima Katsuraba, Charlotte Walling, etc. So they also sort of give different proof, for example, for this type of sets, lambda n. And more recently, Saha established a result for degree 2 Siegel cusp forms. Now notice that the set that he finds is smaller than the one that Saguier and Yamana have in the degree 2 case, because T is not only primitive as before, but it's fundamental, which means the determinant of T times 4 is a fundamental discriminant, minus that is a fundamental discriminant. So in some particular, he put some restrictions. If big N is square free and K is even greater than 2, then for this type of Siegel cusp forms, this delta 2 is good. Okay, primitive and fundamental. I don't remember exactly the year, maybe 2013 or something like that for this result. Okay, later on, actually in 2020, I published a paper with a different delta set. Here we have the conditions: n odd and square free, k integer even greater than 2, and a character chi of conductor n. In that situation, you can prove that if f is a Siegel cusp form in this space of cusp forms, then there are infinitely many primes numbers p and infinitely many square free positive integers n, such that the coefficient indexed by t with t of this type is non-zero. So here you have a diagonal matrix, and you can specify that this lower right entry is a prime. So in other words, you can show that this set delta 2, consisting of the diagonal matrices, also works for the cusp forms of degree 2, provided k and n satisfy the conditions in the theorem. And here you have then a different set that also works. Of course, this set delta n, of course, don't have to be unique. Of course, there could be many different ones. Okay, so this is what we have so far. That's what we know so far. Any questions?
Yeah, but an infinite number of coefficients also can be zero. For example, for this the T matrix that you have written, there might be infinite number of prime P and the n such that this coefficient is zero.
That's correct. That's correct.
The other ways also might be true.
Right. I'm not claiming that all coefficients indexed by such a matrix is non-zero. No.
Okay.
But remember that the equivalence that I showed you before, if I prove a statement like this, like the one that is in the theorem, I can say, okay, if you look at the coefficients indexed only by diagonal matrices, then you can identify F completely. So that's the goal if you want. And I want this set of coefficients, I mean the set of index, to work for every big N and every character chi and every weight k. So that's why this set has to be infinite, even though each particular vector space for a given k, a given n, and a given chi is finite dimensional. So strictly, for each of them, you only need finally many of these coefficients to identify the cusp form. But if I want to work something that works for all of them, for many of them, you need an infinite set. Okay, so everything up to now is what we knew up to 2020. So of course, after that, after this result, I set myself the goal to try to generalize this statement, this theorem, and I got partial results. Ideally, I mean, one would say maybe it's true. I don't know. If for any n instead of 2, the diagonal matrices is a good set, index set. But that I don't know, and now I believe that maybe such a set is too good to be true. It's maybe one doesn't have that. I'm not so sure, of course, but maybe diagonal matrix is for an arbitrary n instead of 2 is not good enough. But I have some partial results, and I will show you those. Something else. Recently, Boscherer and Das extend Saha's result, but now for Siegel modular or Siegel cusp forms, which have vector value. So they are functions that go from Hn, not to C, but to C to the n, a vector of values, not just one. And then they say essentially that if T is in, but that is for the full group. for gamma n. And they say essentially that the good set of indices are the ones that are fundamental. In other words, that the 4 times the determinant is a fundamental discriminant, sort of. Yeah. Okay. So what do I have now? At this moment, I can say the following: for n odd and square free, and for k greater than 2 even, and any character, sorry, the character has to have conductor equal to the level, equal to this big N. Then, if the Siegel cusp form is non-zero, there are infinite prime numbers p and q, different p and q, and a half-integral positive definite matrix T2 primes, such that the coefficient CFT is non-zero with T of this type. You see, the last column and last row is 0 except to the right entry, which is the prime P. The other column, the before the last column, is almost all 0 except that it's a delta here and the prime Q. And delta has two choices, or is 0 or is Q. And so far I cannot say more about the other block, the n minus 2 by n minus 2 block T2 primes. I cannot say much. Of course, I will tell you at the end that maybe there's something else that you can do with this other block. But so far, I have this statement that I can prove, and it's a step in the direction that I want to get a result, of course. But I don't have the full answer yet for an arbitrary n. Of course, if n is equal to 3, I can say something, right? Because then this matrix T2 primes is just a 1 by 1. So I have some advance from my previous theorem. But for general n, still there is a way to go. Okay, so now what I want to do is sort of give you a sketch of the proof. And I don't know if you have any questions.
Do you determine these primes explicitly? I mean, or
the determinant, of course, in the case of 2 by 2 is just n by q, n by, right? I mean, if you go to the previous slide.
no. What I mean that this prime p and q, you determine them explicitly. I mean, it's
Oh, I see. Sorry, yeah, I didn't understand the question. No, I just can say that infinitely many primes that do that. But I mean, I can, yes, I have some, I can say things, but some basic things. Like, for example, I can choose P to be bigger than big N. And then choose Q bigger than P. Because at each stage, I know that it's an infinite many primes with some property. So for that reason, I can choose the corresponding prime bigger than something, for example. So I could say that I could get an increasing sequence of primes, each one larger than the previous one, such that something happens. But I cannot say more. In fact, you will see in the idea of the proof why this is so. So the sketch of the proof is the following. Remember, what I have is a cusp form in this space S, the weight k on gamma 0 n character chi, which I know is non-zero. I have to find in the Fourier expansion of that Siegel cusp form a coefficient that is non-zero, that is for sure non-zero. Yeah. Okay, so how we do that? First of all, I use part of the hypothesis. If you remember, in the hypothesis says the conductor of the character is equal to this big N. And now, if you remember Yamana's result, it says in this Fourier expansion, there's at least one coefficient that is non-zero indexed by t, where the GCD of the matrix T divides a quotient. The quotient of this big N divided by the conductor of the character. But I put myself in the situation where this quotient is 1. So I can say that there is one Fourier coefficient indexed by t, which is non-zero, where t is primitive. In other words, GCD of t is 1. So I use Yamana's result and I get that. Now let me say something a little bit, take a little detour. Every matrix T in this Jn, this half integral n by n positive definite matrix, define a quadratic form in n variables. So that's a matrix T that's define a map from C to the n tuples, to C, to the integers, and in this way, x go to x t x transpose. It's a quadratic form, an ordinary quadratic form in n variables. And since the GCD of t is 1, this is a primitive quadratic form. Okay. In the case of n equal to 2, when it's a binary quadratic form, Mertens and Weber in the 1800s, at the end of the 1800s, like more than 100 years ago, they proved that for n equal to 2, the binary quadratic forms, primitive binary quadratic forms, such a quadratic form represents infinitely many primes. That is to say, there are tuples n1 and n2 tuples in C2, such that x times t times x transpose give you a prime p. So this is a very classical result, and I look for the generalization to any n, to any quadratic form in n variables. And to my surprise, I couldn't find it in the literature. I asked a couple of experts in quadratic forms. I'm not an expert in that subject, and I asked them, and they give me some ideas of how this could be true, but they didn't mention any paper. So I believe that, I don't know, but I believe that there is no, this result for any n is not in print, even though some people told me that it's probably true and probably is not difficult to get. Anyhow, for some, using some inductive arguments, I was able to extend this statement by Weber to any n. In other words, I know that a primitive quadratic form in n variables represent infinitely many primes. I don't know which ones, but I know that infinitely many primes represented by such a quadratic form. Hence, if before I know that there's a Fourier coefficient indexed by t, primitive t, which is non-zero, I can say that such a t represents infinitely many primes. Okay? So I can say something about this t that is special, right? Represent infinitely many primes. Suppose that p is one of these primes. So this means that if I take t and I conjugate t by G, some matrix in SLNZ, I get a matrix that looks like this. In the lower right entry, I can put P here. Therefore, the coefficient indexed by such a matrix is the coefficient, of course, indexed by the matrix G transpose TG, And we knew already that this coefficient has the same value that the coefficient indexed by t, which we know is non-zero. So now we conclude there is a matrix whose lower right entry is this prime p, such that the coefficient indexed by such a matrix is non-zero. So I have something. So the type of matrix that I'm looking for, I already have something. I already know that this lower right entry is p, a prime. And in order to see that this matrix is more specific, looks like, I mean, I can say more about this matrix. I have to do some particular manipulations, and this is what I show you now. Now I look at C in Hn written in this way. I write it in blocks, such a way that the tau here, the lower right entry, is a 1 by 1 block. Therefore, C prime is a n minus 1 by n minus 1 block, and so on. So I break the C in Hn into 4 blocks. And the same thing with T, which is an n by n matrix, right? I break it into 4 blocks. The upper one is n by n minus 1 by n minus 1. The m is a 1 by 1 block. If I do this, the same Fourier expansion that I have at the beginning can be written now in a different way. Somehow I isolate what happened with the exponential at m, at tau, and I have everything else, I put it in a series, which I call little f sub m. Now this function is a function in the variable c prime and w, and has a Fourier expansion. Of course, whatever is left from the Fourier expansion of big F, if you isolate the exponential to the m tau. And what happened is such a series is not a Siegel modular form anymore, but it's a Jacobi cusp form. It's a Jacobi cusp form of weight k, index m, and character chi, over a group that has to do with the original group that is not the same, of course. Before was gamma 0 n. Gamma 0 big N of degree small n. And now you have a gamma 0 big N, but degree 1 smaller, n minus 1. And there is this lattice, c to the n minus 1 times itself. So what happened, if you go back, you will see that the Fourier series of this small f, f sub p, for example, have Fourier coefficients which are also the Fourier coefficients of big F. Therefore, the argument before says that this Fourier coefficient, which is non-zero, indexed by a matrix with lower right entry P, which means this, instead of M, you have a P, and the Fourier coefficient of that is indexed by that is non-zero. But that Fourier coefficient is within the Jacobi form little f sub p. So that's why what you knew before, what you know from before, implies that little f sub p is non-zero. So now the Fourier-Jacobi coefficient little f sub p is non-zero. In other words, if the Siegel cusp form that you start with is non-zero, has infinitely many primes p associated, such that these Jacobi forms f sub p are non-zero, because you know that at least one of those coefficients is non-zero. And now you deal with the theory of Jacobi forms. The Jacobi forms, or every Jacobi form, can be decomposed as a sum of functions where they are a particular function that I call little f p sub mu and a theta function. The theta function is a classical theta function on the Siegel space, and it's given here. Okay. And so we have a Siegel cusp form big F give you many non-zero Jacobi forms little f sub p, and each of them can be decomposed in finitely many terms involving the theta function and some coefficients in front. Okay. You know that fp is non-zero. The little fp is non-zero. Therefore, in this sum, at least some of the coefficients f sub p mu must be non-zero. And so these components, f sub p mu of the Jacobi form, you have some automorphic form properties. And all of them together define a vector value Siegel cusp form of weight 1/2 less. So if the weight of fp, the Jacobi form, is k, the weight of the Jacobi form fp components is k minus 1/2. Okay, now let me recall a Tether relation proved by Yves in the 60s, I guess, or maybe 70s. It says that when you act with the group gamma n, or in this case gamma n minus 1, on these theta functions, you get a relation involving the other theta functions indexed by the other mu's, say, and some coefficients. Okay, so these coefficients u. Okay, you can compute those coefficients. It's not simple, but it's just a technical thing. And the point is that this relation that I described with the function theta, the collection of theta functions, implies that something similar occurs with the theta components f sub p mu. So in those relations, always you also have these coefficients u, mu, nu of m. So if you know them, you can say something about the theta components. And by a technical argument, you know that if the Jacobi form fp is non-zero and n is odd, you can prove that this particular theta component, the one indexed by the tuple mu equal to 0, 0, 0, 0 n times, or n minus 1 times, that theta component is also non-zero. So far, what do we have? Big F, a Siegel cusp form of weight k on gamma 0 n, character chi, where n is odd and the conductor of the character is equal to n. It means that it has the Jacobi form f sub p non-zero for infinite many primes p. We have that. And by the argument that I just told you, you can prove that, and for each such Jacobi form, its zeroth theta component, f sub p0, is also different than 0. But now, the Fourier coefficients of this theta component f sub p0 are indexed by matrices of this type, a block, an n minus 1 block, T prime, and last column equal to 0, except in the last place where it's P. So, since the coefficient of this theta component fp0 have to do with the matrix, with the Siegel cusp form, the original Siegel cusp form, big F, you can prove, or you already have then, that the Fourier coefficient indexed by this type of matrices is non-zero. So you get that the Fourier coefficients of the original Siegel cusp form indexed by these matrices is non-zero for infinite many primes P. Okay? And now that you already got this, you see you have a good description of these matrices T, at least for the last column and last row. And the idea is to do an inductive argument and do something similar in order to get information about the other columns and rows of the matrix. So now, instead of big F, which is a cusp form of weight k on gamma 0 n and character chi, the one that we start with, let's do the same thing with this other object, this theta component of the Jacobi form involved in the Fourier-Jacobi decomposition of the original one. In this case, since f sub p is a Jacobi form of this type, its zeroth theta component is a Siegel modular form of 1 degree less. So it's not just a small n, but a small n minus 1. So it's in a group of degree, in the symplectic group of degree n minus 1. The weight also changed. Instead of k, is k minus 1 half. That's why I have to work with this type of Siegel modular forms too. And now the gamma 0 n also changes. Now instead of big N, I have the lowest common multiple of big N and 4p. The same p that I had before multiplied by 4. And then there's a different character too. I can be very explicit about the character, but I don't care at this moment. But you see, I have solved the same type of situation than before, except that now the weight is half integral, which means that the theory is a little bit more complicated, but it's not a big deal. It's not a big problem. What is a big problem is that now the level, the gamma 0 n, is replaced by gamma 0 of this lowest common multiple of n and 4p. No, so now this is not odd anymore. And so that will be a difficulty, a more important difficulty for what follows. So if I do exactly the same than before, well, except that I have to take care of these problems, the previous argument yields the existence of infinite many primes q now, such that this series is such that the Jacobi forms fq prime, which appear in these Fourier-Jacobi decompositions, are non-zero for infinite many primes q. So now I can say there's a matrix of this type which indexes a coefficient of f which is non-zero. So now I have a q as before, as I wanted, but now what is this column? It's not clear that is zero. I'm running out of time, so let me just one more minute and I'll be finished. I cannot prove that these are zero because now this number is not odd, remember? So, but now one can do something else, namely, I can prove that if the first theta component is zero, so it's not what I want, then this other combination of theta components for fq prime is different than zero. And if that's different than zero, then you can show that this theta component, this particular one, indexed by mu of this type, this is non-zero. So here I'm finishing. I can show that if f is a Siegel cusp form in this situation, then either fq0 is non-zero or fqq is non-zero. And each of these cases give me these matrices. Okay, and so in that case, there is a coefficient in each of them that is non-zero if they are non-zero. Therefore, I can obtain what I claim. And that's it. Thank you.
Okay. Thank you.
Thank you. I'm going to take this out.
Roberto, ¿quieres
Okay,
tomar?
thank you very much, Yves, for this nice talk. Are there any questions?
Maybe is it useful to consider a small class of cusp form, for example, eigenforms? I mean, they are apparently eigenforms are much useful than general.
That's correct. I mean, you for sure one can. I mean, these are much more specific cusp forms, but in all these arguments, the Hecke operators don't play any role.
Okay.
So I don't know how to using the same argument try to conclude something, because I don't know how to make them to play a role.
Because, for example, Hecke operator in the case of classical modular form, at least they if you have an eigenform, the coefficients of primes, they determine all the other coefficients. I mean, this is a
That's true. That's correct.
That is, I mean, something good with the at least eigenform. And
that's true. But in any case, in that situation, that this I guess I can say. In the case of the classical case, the coefficients are the eigenvalues somehow, and the eigenvalues are indexed by integers. In the case of Siegel cusp forms, the coefficients are indexed by matrices. So to me, it's not so clear that something indexed by numbers are enough to give a full description of a Siegel cusp form somehow.
another thing, maybe, okay, I can. For example, in the last 4 or 5 years, when I was talking with physicists, they were computing some stuff. I don't know what they were computing, but at the end, it was becoming a Siegel modular form. And I was thinking, well, I don't remember if it was a cusp or not, but at the end, it might be interesting to see if your results is a kind of non-trivial for this specific Siegel modular form that they were interested. At the end, I think at the end they are interested on Siegel modular form because of the coefficients or some enumerative meaning. Yeah, but this is just a kind of vague direction.
Yeah, but I understand, and I believe that, of course, I have no idea how to do that, but somehow, if what I believe is that you eventually can end up with a set of matrices which have diagonal blocks, 2 by 2 blocks in the diagonal. Everything else is 0, and these 2 by 2 blocks are in the main diagonals are primes, and off the diagonal are zeros or primes, something like that. But the point is that if you know that those Fourier coefficients determine the Siegel modular form, the Siegel cusp form, it means that these Fourier coefficients have somehow all the information that you carry in the Siegel modular form. Therefore, if in some situation, I don't know, algebra or physics or analysis or combinatorics, these coefficients tell you something special, you can say, okay, these coefficients have information that that combine all the information from the other places. I mean, they carry intrinsically, they have all the information that all the Siegel cusp form carries. So but that's a different thing, right?